And in just a few minutes, we're going to cover the quiz that you guys are having in class, in the classroom on Friday. Thank you, Robin, for doing it. I should get those quizzes in the mail or on the shuttle later today, so you should have them tomorrow. So I appreciate you covering those two quizzes for me on Friday. So it's the quiz that you guys have. I will go over that here in just a second, but I want to keep us straight on what we've got going. So I'm going to move over to the computer, see how things work. So when you go into WebAssign, you should have these assignments that are out. The homework for simple harmonic motion is due Friday at 6 p.m. And we've been covering that now for the last two class periods, and this class period we'll actually dive into a little bit more. And we're going to start talking about waves and that kind of thing, so you should have those pieces. And that's chapter 13, by the way, for those of you that are wanting to know exactly where it is in the book. It's chapter 13. Also, if you looked at the original dates for like the sound homework and some of the pre-work, it looked like it was all due this Friday. It's all been shifted because we haven't even started sound yet. So it's been shifted to next Friday, and then we should start electrostatics probably that first full week in February. So, and which means we're going to have a test over sound and waves that first week in February as well. So just kind of giving you a heads up as to exactly where we are and where we're going. And then you've got some interactives and supplemental problems that are kind of due towards the middle of February. So we've got some things that are happening, and I'm working towards that. So that's in WebAssign. If you caught it yesterday, you got pinged. I've got in here an introduction to waves. That's really kind of a cool one because it really is going to show how something traveling on a wave is going up and down rather than moving along the wave and then talking about the velocity of the wave. I also have one about sound in there to start along with there, and how the human ear works, and something really cool about synchronized pendulums. So it's in there looking at the synchronized pendulum. So you've got quite a bit of resources in addition to the past lecture periods that are also there. So that gets it. I will not be here on Friday. I am going to be traveling to an American Chemical Society meeting, and so that's why you're getting a quiz on Friday. So the quiz on Friday is going to be a little different, okay? There will be no cheat sheet. You're not allowed to have a cheat sheet. And I'm asking that you don't use a calculator, which means if you were to be given a situation like this, okay? So I've got that I have a position versus time equation, and it's 5.8. We're going to use cosine 8 pi. Oh, I'm not going to do that way. I'm going to do it a different way. We're going to do it as 0.8 t plus pi over 6. Okay? And you're asked to give me the amplitude. You should be able to read it right off. So the amplitude on this one is 5.8. You're asked to give me the angular frequency. That's omega, and omega is going to be 0.8. You may be asked to give me the frequency, but remember that omega is equal to 2 pi times the frequency. So this is going to be omega divided by 2 pi. I will accept the answer in this format because I am not asking you to calculate it out. Okay? Because I don't necessarily want you to have a calculator. Now, some of the numbers may make it easy for you to do the calculation, but that's great, but you can leave the answers in terms of 2 pi. So if I do period, period is going to be 1 over the frequency, so the period for this is going to be 2 pi 0.08. And that will be an acceptable answer on the quiz. Okay? So you can leave it in there. So no calculators, no cheat sheet. Which means you're going to have to remember a couple of things. Means you're going to have to remember that the general wave equation, I'm going to do it in terms of x this time, is the amplitude cosine omega t plus a phase angle. The velocity as a function of time is going to be minus a omega sine omega t plus the phase angle. Making sure I'm doing it all right. And then the acceleration times time is going to be minus a omega squared cosine omega t plus the phase angle. You're going to need to remember that omega is equal to 2 pi times the frequency. And that omega squared is equal to km. That's omega squared, sorry. Omega squared is equal to km. You'll need to remember how to calculate the spring constant. F, the magnitude of the force, is going to be equal to kx. You'll need to remember that the potential energy of a spring is 1/2 kx squared. So, if you've been working on the homework, these should be pretty familiar to you by now. You'll need to be able to pull information. If I give you the wave equation, you'll need to be able to pull information out of it. And if I give you a graph, be able to plug the information into it. And you'll need to be able to tell me things like the amplitude and the period, label that on a graph, or label the amplitude and the wavelength on a graph. So the quiz has 10 problems in it. I think it should be pretty easy. Okay, I think it should be pretty easy, and it's covered everything up to what we've had done to right now. So some of the stuff that we're doing today will reinforce this, but things like the pendulum equations and things like that will not be on the test or the quiz. So it's worth 50 points, and it's going to count as a quiz. And remember, I tend to drop a quiz. Okay. Questions? All righty, we're going to dive in. We're going to dive into stuff. Okay. So on Friday, we finished up, and I did get everything posted. So on Friday, we finished up with doing the piston problem and looking at the velocity of the piston and the acceleration of the piston and looking at those things where we could read information from our equations. But now I want to look at kind of looking at the spring and looking at work and looking at the motion, so looking at the energy. So what we have is we're going to have a spring system. And it's going to be moving back and forth. And we talked about where the velocity was going to equal 0. The velocity is going to equal at the top and at the bottom of our system. So if this is the bottom, the velocity is going to be 0. And if this is the top, the velocity is going to be 0. And the maximum velocity is going to occur as it goes through position equals x equals 0. That's where the maximum occurs. And we talked about the potential energy of our spring is equal to 1/2 kx squared. And remember that work and energy are related. So I could be looking at the work done to pull my spring all the way to the end. I can actually be looking at that. So if I did it this way, looking at our spring, and we have it bouncing up and down this way, the total energy at the top is going to equal the potential energy. The total energy at the bottom is going to equal the potential energy. And right through the middle, that's going to be the kinetic energy is going to equal the total energy. So very much like what we've done before when we've dropped a ball off of a building, we've been able to get this going back and forth. But if I look at this, let's kind of look at how this works. If I have kinetic energy is 1/2 mv squared, but now I'm going to substitute in that v as a function of time. That's going to end up being 1/2 ma squared omega squared sine omega t plus my phase angle, and that's squared. Now, remember we said that this is my velocity, so when I square it, the negative goes away. So that's why I get my a squared, my omega squared, and my sine squared. I'll bring it back up here in just a second. So I've got that velocity right there, and now when I put it in for my kinetic energy, I get this lovely right here. Now I'm going to do the same thing for potential energy. So my potential energy is equal to 1/2 kx squared, which is 1/2 k, and my x is a cosine, a cosine omega t plus phi squared. So I'm going to get 1/2 k a squared cosine squared omega t plus phi is going to be my potential energy. So if I write out total energy, okay, total energy as it stands right now, I get 1/2 a squared m omega squared sine squared omega t plus phi plus 1/2 a squared k cosine squared omega t plus phi. So that's my total energy for the system. Now, we can simplify this, make it a little easier on ourselves by doing a couple of things. Is it hot in here to you guys?
It just kicked on.
It's roasty. Okay, one thing we do know already is that omega is equal to k over, or omega squared is equal to k over m. So what I'm going to do in here is I'm going to put a k over m in here. I'm going to factor out my 1/2 a squared, okay? So I'm going to factor that out. And I'm going to get omega squared is k over m, m's cancel, and I get k sine squared omega t plus v. I get k cosine squared omega t plus v. Well, now I can factor out the k. And I'm going to get 1/2 a squared k sine squared omega t plus v plus cosine squared omega t plus v. And hopefully sine squared plus cosine squared looks very familiar. What is sine squared plus cosine squared?
1.
1. So I end up with the total energy of a spring system is going to end up being 1/2 Ka squared. Okay? But that's also equal to 1/2 mv squared plus 1/2 kx squared. And if I do this to solve for v, I want to find the velocity of my system at any given time. I'm going to solve for v. I can get rid of the 1/2, so I can get Ka squared is equal to mv squared plus kx squared. So I get Ka squared minus kx squared is equal to mv squared. I get Ka squared minus x squared, x squared divided by m is equal to v squared. So v ends up being the square root of Ka squared minus x squared divided by m. That will give me the velocity of a spring system at any point throughout the oscillation.
So it's the spring during any point of the oscillation?
That's the velocity of my end of my spring, because remember my spring is doing this. It's going back and forth. It's going to give me the velocity of this end at any point based on my spring system. Okay. Now, a pendulum can act like a simple harmonic oscillator. Okay? Our pendulum can act like a simple harmonic oscillator. And back from physics 1, we know that F is equal to mass times my acceleration. And this was going to equal mg sine of theta when I looked at my pendulum swinging, because this was my tangential acceleration. And if we're looking at this with an angle and we make an assumption, and if you guys remember the assumption, we make the assumption that the angle is approximately equal to the sine of the angle, and that's when this angle is small. And generally that means it's less than 20 degrees. Okay? In general, that means it's less than 20 degrees. And when we do that, we get any point along this curve S. This is going to be the length of the pendulum times the angle. And we kind of went through the whole thing, and we showed that omega is equal to the square root of gravity divided by the length of my pendulum. Or the period was going to be 2 pi over omega, which meant that the period, when we did this, ended up being L divided by G. So we could use a pendulum, and that's how we actually talked about it. We can use a pendulum to actually give us the value of G. We could go back and give us the value of G. And this is for a simple pendulum, and remember the simple pendulum is essentially a washer or a weight on a small string. So the string did not influence the system. Okay? The string didn't influence the system. But now we know a little bit more about things. You know, we've been working at this for a while, so we know a little bit more about things. So let's look at the system a little differently. So I'm going to keep my simple pendulum page here. Now let's do what we call a physical pendulum. Okay, a physical pendulum is going to be more like my grandfather clock. So in my grandfather clock, I might have a rod, and then I've got a pretty big weight sitting out there, right? And it's going to have a center of gravity, and it's going to go back and forth across this to actually calculate my time. And I'm going to actually give this some dimensions here. That's going to be 1/2 meter for this, and this piece right here is a whole meter. Okay, that's a whole meter. And for a physical pendulum, I have to worry about the torque because I have to worry about our lovely moment of inertia and our angular velocity. So in a physical pendulum, I have to deal with this. So if I do that, remember torque was my lever arm times my force. That's going to be my moment of inertia times my angular acceleration. I can go back and show that my angular acceleration is going to be r mg radius divided by my moment of inertia times my angle. And I can write for my physical pendulum something that's very similar. This is mgr over I. And that r is the distance to the center of mass. Okay, that r is to the distance of center of mass. So if I were doing a physical pendulum that's just a rod, that's what I would be using. I'd be going, here's my distance to my center of mass. Now remember that we have, back in that chapter, you've got tables of what the moments of inertia are for various objects, whether it's a sphere, a disc, a rod, any of those kinds of things, we're going to get that physical pendulum. So I'm going to take this situation right here. I'm going to rewrite some things so that we've got it kind of keeping track here. So I've got a physical pendulum. We now know that omega is going to be related to mgr I. And once I have that, I can do that the period is 2 pi, the moment of inertia, mg, to the distance to my center of mass. Now, if I have a situation like this, we can calculate the combined moment of inertia for that system. And this uses the parallel axis theorem. And we didn't spend a whole lot of time on this in Physics 1, partially because I don't have a whole lot of time. But it is in the book where you can look at the parallel axis theorem, and basically what it says is that I is going to be the I center of mass plus whatever my mass is times my distance, and so I can use it to shift. And so when I have a rod and I have a cylinder, what this is going to give me is my 1/12, the mass times the length of the rod, plus m times my center of gravity, or center right there. And this is mdl squared, and that's squared. I think I forgot to put the square. Yep, I did. So if I'm shifting this pendulum down, I can use the parallel axis theorem to actually calculate it out. And if I do this, and I've used my numbers for my L and my D that I've already got, the length of my rod is 1, and I've got this to the center of mass, which is now 1, I end up with that this is 1/12 m, and this is going to be 1 squared plus m1 squared. It's going to end up giving me 13/12 m for my I. Now I'm just going to plug that back in here to calculate the period. Okay, calculate the period, and that's going to give me T is equal to 2 pi square root of 13/12 m mg1. Since I know g, this gives me 2.09 seconds when I plug it into the calculator. So this is the calculation that we get for the physical pendulum. Now, if I want to compare that to our simple pendulum, okay, so I want to compare that to our simple pendulum, that's going to end up being 2 pi, the length to the center of mass, right? It's going to be 9.8. This ends up being 2.01 seconds. So if I assume my system works as a simple pendulum, it's 2.1 seconds. If I assume my system is a physical pendulum, I get 2.09 seconds. And if I did a percent difference to kind of compare these two, that's going to give me 4.08%. So my physical pendulum actually has a longer period than my simple pendulum, if we assume that the system behaved like a simple pendulum. And it doesn't, because we've got a mass distribution throughout. So I'm going to do a biological example where we want to use a physical pendulum to work for us. Okay? I'm going to use a biological example. So what I'm going to do here, and we all know my artistic abilities are not all that great, right? So I've got a person. And I've got a person, and this person is a little oddly shaped. But I've got a person, and this person's leg is going to behave like a physical pendulum. So for those of you that may be headed towards physical therapy, this is a pretty logistical type problem. So we're going to assume that this leg is going to behave like a rod, okay? And if it behaves like a rod, then the moment of inertia for this leg is going to be 1/3 ml squared. And we're going to look at the from here to here, which is we're going to make the assumption is the center of mass, that the height is 0.37 meters. the mass of the leg is 6.5 kilograms. This is if it's a rod, but then we're gonna measure the period of this thing. So we're gonna measure that period of 1.2 seconds. This is actually how you can calculate a moment of inertia for an oddly shaped object. Okay, and we're gonna compare it to that. So I'm gonna use that T is equal to 2 pi square root of I m g h. We know m, we know h, we know t, we don't know I, so we're gonna solve for I. So I ends up being t squared m g h divided by 2 pi. If I plug in the numbers, I get 1.2 seconds squared. I get 6.5 kilograms. I've got gravity. I've got my 0.37 meters divided by 2 pi. I get I equals 0.86 kilograms meters squared. If I plug in the values for my system, this would be the length of the rod, and the length of the rod is 0.88 meters. So the length of the leg is 0.88 meters. So if I do that, I get I is equal to 1.3, 6.5, my 0.88 squared. That equals 1.7 kilograms meters squared. So it's a big difference if we assume the leg acts like a rod versus what the leg actually does. It's a very big difference. It's almost twice. That's 1.7 and this is it's almost twice. So looking at things as physical pendulums make a big difference. So let's look at another physical system. Now we're going to also use it to start talking about waves, okay? We're going to use it to start talking about waves a little differently. So I have a buoy. And if we all know how buoys work, okay, they're either tied to the bottom of the water or something along this way. And then here's my surface of the water. Now, if we have a wake, we're going to get a wave, okay? Except this time my wave is going to be traveling with a velocity like that. So my object, the wave is going to come by, and it's going to travel, and a wave will actually travel, and we can look at a wave as a pulse. And we can look at this pulse traveling down a rope, or traveling a variety of things. But if I'm in the water, we know, and we've had this experience, what's going to happen to our buoy is stationary, but it's going to go up and down. So even though the wave is traveling this way, the motion of this buoy is just going to go up and down. That's all it's going to do. So we're going to look at this cylindrical buoy. It's going to have a mass of 40 kilograms. It's got a cross-sectional area, so that's bottom here, its cross-sectional area is 0.03 meters squared. And in this case, we're going to look at the amplitude as being 15 centimeters. So it's going to go down, when it goes to the bottom, it's going to go down by 15 centimeters. We want to know what is the period of the oscillation. So we want to to know what is the period of the oscillation. Reason I went and did this is because in this case we have to account for the water. Okay, we have to actually account for the water. And so the force, the buoyant force that we're going to have restoring it is going to be the density of water, gravity, the amplitude, and the area times the height, because that's my volume. It's equal to the area times the height. And that's my buoyant force. That's going to equal mass times my acceleration. And if it acts as an oscillator, my acceleration is km/x. And I end up getting my period is equal to 2 pi m/k. Now if I solve for this, right, if I solve for acceleration, I get acceleration is equal to rho g amplitude x divided by m, which is equal to k m x. X's cancel, m's cancel, and that's where I get, so I end up with that lovely, and that gives me k is equal to rho ga, which is what I'm going to plug into there. So I get the period equals 2 pi square root mass divided by rho ga. And this is 2 pi square root 40 kilograms. Density of water is 1,000 kilograms meters cubed. 9.8 meters per second squared, and I get 0.03 meters squared, and that works out to be about 2.3 seconds. So it gives you a little bit different system to kind of look at. Okay, we good? You guys good over there in Enid? Alrighty, so now let's start talking about waves. Like I said, using that one to kind of start us gives us a better idea. So waves carry energy, all right? Waves carry energy. And usually how we start out talking about waves is we take a stream. Okay, so I've got a stream, and we're going to send a pulse in that stream. Okay, and you've seen somebody do it. We get a pulse sent in that stream, and the pulse will move down, and depending on what it encounters over here at the end, it'll do a couple of things. If this end is fixed, okay, it's fixed to the wall, my pulse will go and it'll hit, and then it'll return, it'll flip over, and it'll travel back like that. So that's one of the things that happens, okay? It's one of the things that happens. How fast this pulse goes through is going to be related to some things about the string. It's going to be related to its tension of the string, and it's going to be related to what we call the linear density of the string. And if you're playing with the muscle ropes, you know how hard it is to get a pulse to go down some of those muscle ropes, right? If you've ever done a muscle rope, trying to get a pulse to go down that string is going to be very different depending on the tension and on the linear density. And it works out that when we're looking at velocity, the velocity as it goes through is going to be related to the tension in the string and our linear density. You guys can go through the chapter to actually look at this. I am not going to focus a whole lot of attention on this part because it's going to come back to look at a variety of different things. But just know that how fast my wave is going to go relates to my tension on the string divided by this linear density. That's important because when we get to sound, we're not talking about just a string anymore. We're talking about the medium in which the wave goes through. Because there are two types of waves. We have what we call mechanical waves. And a wave going down the string, or a wave in water, or a wave like a sound wave, those are mechanical waves, and they're going to require a medium in which to operate, be it the string, be it air, be it steel, be it wood, be it something. Mechanical waves are going to require that we have a medium. Then we have electromagnetic waves. And in an electromagnetic wave, I don't have to have a medium. And the classic example that we use talking about our mechanical waves and our sound waves, and I'm sure everybody's seen this experiment somewhere along the line. You have a glass jar, and in that glass jar you have an old-fashioned bell and a hammer that's going back and forth for this, for my clock. I've got an old-fashioned alarm clock, and if I pull a vacuum on this, if I pull a vacuum on this, what happens?
Doesn't make sense.
It doesn't make sound. You know, when we start out, if we've got air in there, we hear the bell, the clang, 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 but as we pull the vacuum, the sound totally disappears. Because it has to have a medium in order for the sound to travel. So if I'm pulling a vacuum, sound is a mechanical wave, and that's why we start this part out. This sound is a mechanical wave. Now we just talked about two types of waves based upon whether or not they have to have a medium. So mechanical waves have to have a medium. They have to have something to transmit it, whereas electromagnetic waves do not. So that's one of the differences. But then we have two types of two types of waves as well, talking about how the waves propagate. Okay? Now, if I'm looking at the surface of the water, or I'm looking at a wave traveling on a string, it's going to look like this. Okay, so we have the wave that's going up and down. This is called a transverse wave. Okay, and it's the wave we typically think of when we think of a wave moving back and forth or going along the wave. We think of that up and down motion because we think of water waves. That's what we think of when we're looking at waves. In a transverse wave, this is my amplitude, just like what we were showing in our simple harmonic oscillator. And from point to point on a transverse wave, if this is distance, okay, not time anymore, this is distance, we're looking at that wave traveling out from some source, this is going to be wavelength. So from peak to peak, trough to trough, the same point to the same point, That's going to be wavelength. And the velocity of my wave is going to equal the wavelength, which is in meters, divided by the period, which is in seconds. And that's going to give me wavelength over period, but then period is also frequency, so it's that right there. This equation is always correct, okay? My velocity for my wave is always going to be the wavelength times my frequency, or my wavelength divided by my period. Things that come into play, because you guys have all seen it, saw it in chemistry, you also see that we can use C is also wavelength times frequency, and this is for electromagnetic waves. Where C is the speed of light. Okay, so the equation is the same, except for electromagnetic waves, I typically know what my speed is. Okay, I typically know what my speed is because it's the speed of light, which is approximately 3 times 10 to the 8 meters per second. But for mechanical waves, I'm not traveling at the speed of light. I'm traveling at whatever my medium is going to give me, and I can look at that speed based on the same equation that we have. Okay, based on that same equation. So transverse waves look like that. Okay? We have a different type of wave that we also work with. Still going to be able to use my velocity as the wavelength times frequency. Except in this case, what happens is, which is why I bring a slinky, I get a pulse that kind of looks like this, and then it looks like this, and then it kind of goes out, and they get separated. So I get where the density of this gets increased, and then this stretches out, and then the density increases, this stretches out, density increases. So it's also called compression and rarefication. Okay, so you'll hear terms compression and rarefication. Rarefication is when it's going to start to get less dense, and this is called a longitudinal wave. And that's why we have slinkies. Because slinkies can demonstrate longitudinal waves really, really well. So here's my slinky. Heavier, got a stapler, so that's going to work. Okay, I've got my slinky here. Let's give myself a white background so you guys can see it. So in my slinky, okay, I can set up a pulse, okay, and let it go, and you'll see that that pulse travels down. See how it's working on here. On the screen. You see how the springs will compress and extend and compress and extend. So I can send a pulse, and this is a longitudinal wave. And what we're going to see is sound as a longitudinal wave versus a transverse wave. So I can send a pulse down there with a longitudinal wave. Now a transverse wave does this. Okay, I get that up and down motion. And that's my transverse wave. My longitudinal wave is a compression, rarefication, compression, rarefication. You'll still get the same kinds of things for wavelength, Wavelength is just going to be the same points on my compression and rarefication, just like I have it on my transverse wave, but I can actually use it going back and forth. So we end up with a variety of different things that we're looking at waves. And waves become really important because we'll start talking about it in terms of we can have constructive and destructive interference. So let's kind of look at that for a second. So I can send a wave pulse, okay? I can send a wave pulse like this, and I can send a wave pulse like this, and what will happen is as they go through, one will show up like, the one will be going like that, this will pass through, this one's going that way. I'll end up with constructive interference, I end up doubling those things, and then eventually I end up with them passing through. This one's continuing on and that one continuing on that way. So this would be what we call constructive interference. This time I'm going to do a wave like this. I've got this one going that direction, but I have this one going this direction. Okay? When they hit the middle, they'll be like that. But when they finish, this one will still be going that way and this one will still be going this way. And this is destructive interference. So I can add waves together. Okay? They actually move and we add waves together. And we all know that we can do constructive and destructive interference because the wave pool at Whitewater is all about constructive interference, getting those waves up. And you know, even if you don't want to admit it, if you had a bathtub at home when you were a little kid, you got constructive interference with the bathtub waves, such that the wave would splash outside the bathtub and have your mother yell at you, right? You know, we all did it. You know, we all did it. We get constructive interference, and we get those things that are working towards it. So we end up looking at those waves going back and forth. But now let's think about what's happening to our buoy again, okay? So if I have a wave that's coming in like this to our buoy is fixed in a position, and so as the wave comes through, it's going to go up and it's going to come back down. So I've got two things that are happening. I've got a wave that's traveling in that direction. I've got something that's going up and down in this direction. And if I'm looking at the position with respect to time of that object, I have to take into account the shape of my wave that's coming up and hitting it. And usually what we do then is we say that y is a function of t. We're actually going to bring that in, that this actually is going to look like sine kx minus omega t. That's the description of how this buoy would be traveling up and down, or it's the description as this wave moves, the motion of this point on the string. Okay, it also describes that motion of that point on the string. Now we can generalize that, just like we generalized it before, by adding a phase angle to it, because it's going to depend on where we start. We can do the velocity in the y direction for this system, and it's going to look like minus a cosine kx minus omega t, if I'm using this one, okay? And then my acceleration in the y direction is going to be minus omega squared a sine kx minus omega. So now this one is a function, this is a function of time, whereas that is my position of my wave that comes through. So it's a little bit different than what we've been doing for our simple harmonic oscillator. Because what we're trying to do is describe the motion as the wave passes through, rather than just looking at the bouncing up and down, okay? In our simple harmonic oscillator, we don't have a wave that's interfering with it, we're just bouncing up and down. In this case, we have a wave that's interfering with our system, and we're having to make sure that we're taking it into account. So we get a little bit differences of equations. Now, you will not have any of this on the quiz on Friday. Okay, you're not gonna have any of this on the quiz on Friday. You've got it primarily trying to deal with your homework that's due on Friday. Okay? Yeah.
So you can see the wave under constructive interference are in phase.
Right, and I was just about to get to that.
So if they're in phase, there will be destructive interference and out of phase.
But
At
there'll
what
be,
angle?
yeah, there'll be destructive interference on out of phase, yeah.
At what angle? 180?
Yeah, well, it's, yeah, when they add together, they'll be just, we always have constructive and destructive interference because you're gonna add the waves together. So for example, let's do this. Let's look at that when we're adding waves together, because this is important when we're dealing with electrical signals or things like that. Okay? So let's send, because I can send a different waveform, all right? So far we've been dealing with waves that look like that. But I can actually send a waveform that looks like this. Okay, so I can send a square looking wave. So I'm going to send a square looking wave. Okay, I'm going to send a square looking wave this way, and I'm going to have it encounter a typical pulse that looks like that. When I get constructive interference for this system, it's depending on the size of my wave, it might look like this. Okay, now if I get destructive interference for that wave system, okay, so I'm going to get this, it's going to look more like that. So it won't necessarily be in that system where we're talking about it being in phase or out of phase. I'm always going to have constructive and destructive interference. Whether it's in phase or out of phase is if I'm perfectly in phase. So I send a nice wave like this, and I'm in a nice wave like this, that when I'm there, this is twice the height. And perfect destructive interference is going to give me flat.
Can you have destructive interference that look like constructive? Where they're right in front of each other and it looks like it's a lot bigger?
No. So think of a concert hall, all right? Let's go into a concert hall. Now, the idea behind a concert hall is to get constructive interference so everybody it gets an enjoyable thing. But there's always a dead seat in the house, right? Always. Because we're going to get a dead seat in the house. And because of that, what's going to happen is we get destructive interference in that spot, and that spot in the concert hall is not really, really good. We do that, we do it on purpose, okay? So we do it on purpose. Has anybody ever been into a sound studio? What do you see in a sound studio? In a sound studio, the walls are, well, they usually have these eggshelly type things on them, right? Because what happens to a wave? If my wave hits, okay, so I've got a wave that comes in and strikes it, it's going to get reflected, right? Well, if I've got a wall that's like this, my waves come in, they get reflected all over the place, and the odds of getting destructive interference increase. Because these waves are going to encounter each other all the time, and they're going to cancel each other out. Which is why you do that in a sound studio. Noise canceling headphones are doing the same thing. They're flooding you with extra frequencies, trying to cancel out the frequencies that you have, that you're hearing. So that's why we do with constructive and destructive interference, is because we want to get that. What'll happen, and we've all seen it, right? So let's say I have a wave that in the water, I drop a pebble in, right? I drop a pebble in, and my waves, when I drop a pebble in, my waves are going to travel out spherically. So I can look at it from the top, and I have it up here from the top, right? So there's my top. Well, I can hit another pebble, and it's going to do the same thing. And we know what happens, right? As it hits these spots, we have areas where they're flat, and then we have areas where they're not. So this is wave behavior, okay? This is what we call wave behavior, where I can have that constructive and destructive interference. Now this is really cool because I think I talk about it in my chemistry class. If I have an object, and I think I just posted one today on Facebook. So this this is a sodium chloride crystal. I have atoms in here. I'm gonna send out X-rays, and they're gonna hit, so my X-rays are gonna hit this, and this is gonna block them, so I'm gonna, and what we'll find out with something called Huygens principle is that each individual point on the wave can be the source of another wave. So what happens in here is once it hits a particle, I'm going to get constructive destructive interference, and I'll get bright dots that tells me that that's a cubic structure. And we'll talk about a variety of those constructive destructive interference things as we move on in sound, because that's what's going to allow us to create, when we talk in sound, it's going to allow us to create a standing wave. It's going to allow us to do a variety of different things. So now let's look at this. So we've got, so if I do this, and I draw my picture really well. So I have, the wave is coming through on a wire, okay? And I have a ring that's allowed to travel up and down here, okay? It's going to allow it to travel up and down. So my position of that is related to this. So I get Y max, which is going to be my amplitude, sine kx minus omega t. And we know that this is going to periodically equal 0, right? We know that that'll periodically equal 0. And when sine of 0 equals 0, that's where we're going to be flat, and we get k omega t is equal to 0, and this will have a variety of potential solutions, okay? There are going to be numerous times where the value of this is going to come so that I end up getting a sine is equal to 0, and typically that's going to happen when that equals a value of pi over 2, or a value of 5 pi over 2, or a value of 9 pi over 2. And these are what we call those, when we talk about wave functions, and we talk about wave solutions, and we talk about wave numbers, this is where we're going to get that information. Okay, that's where we're going to get that information. And so there are various solutions to this problem where the answer is that the wave is going to be sitting there at 0, or the particle is going to be sitting there at 0. And so we get those particular things when we talk about waves and discussions and descriptions that we work with. And that'll also give us that the velocity in the x direction is related to omega k, which we've seen before. So we end up getting a variety of different things when we talk about those waves. What that's leading us to is our discussion of sound, because sound is a mechanical wave. Sound is a longitudinal wave. And we're going to look at sound, and we're going to look at the characteristics of sound, because that's really important as we move forward. And it's going to help us go out there as well. All right, I think that's about where I want to stop today, because I don't want to start diving into sound too much. But I will show you on this one, that's why I wanted to make sure that you guys had this, because this will actually go through, and I got it wait for it to come on the screen, that you can actually go through, and it's a 5-minute one, and it's got really good images of the waves and how those waves look and where those waves come in. And looking at the constructive, destructive interference, looking at the position of a boat on a wave. And this will give you a good start for looking at things. When we come back next Wednesday, we will be dealing with sound. You've got a quiz on Friday. And I think that gets us pretty well where we're at. I'll stop. Questions? Anything else?